So as I said, hi guys, hope everyone is good. Um, we are about to start with our session, and we will be discussing electric circuit, um, Newton's laws, as I said, and hi guys, work, energy, and power. So we'll start with Newton's laws. And we're gonna be looking at a paper from the Eastern Cape. I think it's a trial paper from last year, and then we'll be um, trying to answer this question and also at the same time revising a few concepts in Newton's laws. Right. So before we start, I would like to highlight things that are very important for question 2, and I want you to always uh, remember that this is a chapter that was done in grade 11, right? So it's a continuation of grade 11. So there's nothing new that the examiner is going to bring in this chapter. It's the stuff that he did in your grade 11 or last year for most of you. So what you need to master in this topic, one, are the definitions. So the definitions that you're gonna get in this topic, uh, your laws, obviously, the Newton's laws. You need to be able to define, to state Newton's first law of motion, Newton's second law, Newton's third law, and Newton's law of universal gravitation. So we know that in your exam or your test, the examiner is likely to ask you to define one of the four laws, right? And also you need to be able to define the likes of your frictional forces. Also, you need to be able to define um, your likes of applied forces, stuff like that, kinetic friction and static friction. So those are the few definitions that you get in this talk, in this chapter. And to revise that, you need to go and visit your examination guideline. So all the definitions are stated in the examination guideline. And then 2, it's the drawing of the free body diagram. Free body diagram. So always in this chapter, you'll be asked to draw a free body diagram, right? And these are one of the free marks that you're gonna get. Free body diagram, it's always there in this chapter. So you need to be able to do that, right? You need to draw a free body diagram and you label it in full. And in some cases, they can also ask you to draw force diagram. But we know that force diagram are not popular for exams. So you're just gonna have your free body diagrams, right? And then, so these are the most important parts. And lastly, it's the application of the laws. Application of the laws. So remember, we have 4 laws. So they can ask you about the applications of these laws. So you need to be able to do that. So as we do question 2, obviously we'll be focusing too much on the applications, right? So those are the few things that I wanted you to remember before we start answering this question. And always consult your examination guidelines so that you are able to score full marks for your definitions. So let's try to go to this question and see how we can um, answer it together. So it's question 2. So in question 2, uh, we are given certain instructions, as we can see there. So we need to read the problem description statement, right? So we need to read maybe the problem statement that we're given there, or the description of the question. So we are told that a block of mass 22 kg is placed on a rough inclined surface and is connected to a 15 kg block which hangs vertically by means of a light inextensible string passing over a frictional pulley as shown in the diagram below. When the inclined surface is at an angle of theta to the horizontal, the 15 kg block moves downwards as shown by the arrow alongside the diagram at a constant velocity. So after reading your statement or your question there, your description statement, you need to go to the statement and check if there are important words that the examiner gave you. You need to go and check if there's something that's going to assist you to answer the question. So one of the words that are very important, or words that can assist you to answer these questions, are the words rough. So we are told that this is in a rough inclined. So we identify the words rough, right? So rough simply means that there's friction, right, present. So this indicates the presence of friction. So the examiner might not tell you directly that there is friction in the surface. They use words like rough. So if you see the word rough, automatically you know that there's friction present, right? And then again, we're also told that the um, block or the diagram uh, moves at a constant velocity, right? So if the diagram moves at a constant velocity, it means that so constant velocity. So this tells you that the acceleration at 0 meters per second squared. And if the acceleration is 0 meters per second squared, it means that F net equals to ma, right? So that's what we managed to find from the description, or that's something that maybe was hidden in a way in the description statement, right? So I can see that people are struggling with with network. So I'm sorry about that. It's fine. So we'll just continue. So now we uh, identify that acceleration equals to 0 meters per second squared. So this means that our F net equals to 0. So that's what we're able to deduce from the statement given above. So let's try to answer 2.1. So 2.1 in most cases, or the first question in most cases, are the definitions, right? So you need to make sure that you know how to define or to state all the laws as per the examination guideline. So now it means you were supposed to go and consult the examination guideline for question 2.1, right? Unfortunately, when you are writing, you won't be able to consult the examination guidelines. So as a learner, you need to make sure that you know all your definitions just like that. So they want you to state Newton's law, uh, state Newton's second law of motion in words. So they want you to state Newton's second law of motion, right? So Newton's second law of motion, uh, according to the examination guidelines, states that when a net force, a net force acts on an object. So this one addresses the net force. So when a net force acts on an object, the object will accelerate in the direction of the net force, in the direction of the net force, right? So when the net force acts on a particular object, that causes the object to accelerate, and this object accelerate in the direction of the net force, right? So that's the first part. With an acceleration, so the acceleration with an acceleration that that is um, directly proportional to the net force. So the acceleration is directly proportional to the net force and inversely proportional to the mass. So that is our Newton's second law of motion. So that's given by F net equals to ma. So the first part of this definition, you need to be talking about the force acting on an object, right? So this is the first part of, so the force acting on the object, this has to be the first part of the definition, right? And then how the object accelerates. And then you'll get a mark for that. Then the second part of this definition, you need to be talking about the relationship between the acceleration and the net force and also the mass. And for writing these relationships, you get another mark. So in total, you're going to get 2 marks. So if ever you find yourself in a situation where you only write one part of this definition, it means that you're going to get 1 mark. So to get full marks, you need to write all the parts. So that's fine with the definition. We'll get that in the examination guideline. So now let's proceed to 2.2, which is the drawing of the free body diagram. So I said that you always gonna get these types of questions to draw a free body diagram. So that's 2.2. So they're saying draw a labeled free body diagram of all forces acting on the 22 kg block. So if you go to the diagram and look at the 22 kg block, you can see that the 22 kg block is on an incline, right? So it means that you need to draw a free body diagram of an object in an incline. So how do you do that? So to draw a free body diagram of an object at an incline, you need to at least trace the incline. You can do that using a pencil. You're going to trace the incline just like this, and then you use a dot to represent your object, right? So now you have to start drawing the forces. So the number of forces that will be there in the diagram are usually determined by the marks allocated for that question. So when we look at 22.2, we see that this question has 4 marks. So if this question has 4 marks, it means that we are going to draw 4 forces, right? So it means that we're going to draw 4 forces for 2.2. So let's try to draw those forces. So there are 2 forces that are always there. The first force that we know is the force of gravity. And this force is always acting downwards. So we draw our force of gravity. So you're advised to write your forces in full and avoid using abbreviations or letters. So we have gravity, or you can say force of gravity, right? So that's the first force. And then the second force is the normal force, right? So the normal force is always there whenever an object is on a surface. So we also have the normal force, and the normal force is always perpendicular to the surface. So this is the normal force. So one thing that I would like to remind you guys, I've seen a lot of people uh, drawing the normal force for an object that is hanging. And normal force is a force that acts or that is there whenever an object is on a surface, and this force is always perpendicular to the surface. So if there's no surface, it means that there's no normal force. So that's a reminder to all of you, especially those who are going to write tomorrow, that you remind stuff like that, you remember stuff like that. Then the third force, obviously, we will get it from the information that we're given above. So remember, um, when we read the description statement, we discovered that the surface or the incline is rough. So the rough means that there's presence of friction. So it means that the third force that we're going to draw in our free body diagram is frictional force. So we need to go and draw the frictional force. So it's very important that you know the direction of frictional force. So the direction of frictional force will always oppose the direction of motion. So this will always oppose what? The direction of motion. So what we see here is that we have uh, we have a diagram here that is moving up the incline, right? So if this diagram is moving up the incline, it means that the direction of friction will be down the incline. So this will be our friction, friction, just like that. So that's the third force. So remember, we're drawing 4 forces, and already we have um, 3 forces. So it means we're only left with 1 force. So the fourth force will be the one that goes up. And why is it going up like that? Because we see that these 2 blocks, the 22 kg block and the 15 kg block, are attached by a string. So that string has what? Tension force. So we also have our tension like that. And then we have drawn all 4 forces, and each force gives you 1 mark, like that. So that's how you draw a free body diagram. So you don't have to forget to write your forces in full so that you avoid using letters or abbreviations for the forces. So we're done with the free body diagram. The next question, obviously, is addressing calculations. So what I can indicate here is that for calculation, always you need to use your free body diagrams. Your free body diagrams will always help you to calculate anything that will be asked in this question. So when you start doing your calculations, I can also advise you to draw the free body diagram of the other object on your rough sheet, because you don't know if ever you'll need that to be able to answer the question. So one of the things that I always do is to have all my free body diagrams. So let's see what they want in 2.3. So in 2.3, they're telling us that a constant frictional force of 43.86 newtons acts on the 22 kg block. So now they're telling us that on the 22 kg block, there's a constant force of 43.86 newtons. And now they want us to calculate the magnitude of the angle that will keep the system moving at constant velocity. This is a very nice question. That will keep the system moving at a constant velocity. So before you answer this question, you need to understand the requirement for the system to be moving at a constant velocity. So the for the system to be moving at a constant velocity means that the F net needs to be equals to 0. So that's the requirement, right? So how are we going to answer that? So let's try to answer the question. So that's over 2.3. So they want us to calculate the angle that will make sure that our system is moving at a constant velocity. So what is the requirement? The requirement for constant velocity is F net equals to 0. So that's the requirement. So if that is the requirement, it means that we need to have forces that will give us F net equals to 0. So now let's look at the 22 kg block. So on the 22 kg block, with the information that we have, we can be able to calculate our tension, right? So the value of tension must be the one that will enable the system to be moving at a constant velocity. So the system is the 22 kg block and the 15 kg block. So the 22 kg and the 15 kg needs to be moving at a constant velocity. So what we're going to do now, we're going to use our F net equals to 0 to get something that will give us a 0. So our F net equals to 0, as I've written there, for block 22. So for block 22, or maybe for block 15, let's start with block 15. And the reason why I want to start with block 15 is because I want to get the tension. Because, guys, I hope you can see here that with the information that we're given, for us to be able to get our F net, we need to know our tension. We are given the frictional force, we can be able to calculate our Fg, but the problem now is the tension. So we need to first know the value of our T, or the tension, in that way. And then the value of T can be simply calculated using the 15 kg block. So the 15 kg block, it's the one that is moving downwards, right, at a constant velocity, that is hanging there. So for us to be able to determine our tension, we need to know the free body diagram of the 15 kg block. So the 15 kg block, just like that, it's hanging and it's moving down. So there's force of gravity acting, and also the tension going up. So remember that this thing is moving at a constant velocity. So if it's moving at a constant velocity, it means that F net equals to MA. So if F net is equals to MA, then our F net will be given by, um, we have to take one direction as positive. So we're going to take up as positive or down as positive. So it depends. So I would like to take the direction of motion as positive, and the direction of motion is downward. So I'm going to take down as my positive. So everything that goes down will be positive. So the FG will be positive plus minus T. That's the tension. It will be negative, equals to MA. And then don't forget that our MA is equals to 0 because this thing is moving at a constant velocity. And then this will give us uh, um, minus T equals to minus Fg, right? And this is the same as tension equals to Fg. So that's what we have. And then from now, we need to get the value of T. So the value of T is given by mg. So m is 15, and then g is 9,8, and that gives us a value of 15 times 9,8. It will give us a value of 147 newtons. 147 newtons. So that's our T. And I'm sure at this point, a lot of you are a bit confused. Why am I calculating T? And you'll see it as I conclude this question, the reason I'm calculating my T. Because I understand that for me to be able to get the theta, I must do the F nets for the both objects, right? And the problem that I had is that I did not know the value of T. So I had to get T before I calculate my theta. So that was the F net for the 15 kg, and that helped us to get the tension. So now we're going to calculate the, or we're going to write an equation that will give us the F net for the 22 kg block. So if we look at the 22 kg block, so this is the F net for the 22 kg block. So for the 22 kg block, the F net. So don't forget to take one direction as positive also in this case, right? So we're gonna take maybe up the incline as positive. So if we take up the incline as positive, it means that we're gonna have F net equals to MA, just like that. And remember, this system is moving at a constant velocity. So if this system is moving at a constant velocity, it means that our MA still give us a 0. Then what we're going to do, we're just going to substitute our F net. So for F net, you must always use the forces that are in line with motion. So this motion is up the incline, right? So the forces that are going to be included in your F net are those ones that are in the same line as the motion. So what we see as a hidden force that is in the same line with motion is Fg parallel. Because remember, this component of gravity will produce a, a component called what? Fg parallel. So the forces that are in line with motion here are Fg parallel, friction, and tension. So these are the three forces that are gonna form part of our F net for the 22 kg block. So if we took up as positive, it means that everything that goes up will be positive. So that includes our tension. So the F net will be positive tension plus minus friction plus minus Fg parallel equals to 0. So remember, the tension as the same because we're using the same rope or the same string. We can put it in that way. So the value of tension that we got in the previous calculation of 147 is still the same here because tension is the same. So tension is given by 147 minus the tension that the friction that we're given in the question. I think we're given 43.86. So we have minus 43.86 minus 43.86 minus mg uh, sine theta, because this is FG parallel, right? So this is mg sine of theta equals to 0. And why did I use mg sine theta? Because this question requires us to calculate theta, and I had to come up with something that will give me a theta, or that will make theta part of the equation, and that was my mg sine theta. So we're looking for the theta, and then we have the tension, we have the friction. So all we need to do is to substitute our mg sine theta, and our mg sine theta will be substituted as the mass is 22, right? And then the g is 9,8 sine of theta. So then we end up having something like that. And then we're going to take all the constants to the other side, and then we'll have 147 minus 43,86, which is a minus 103,14 equals to minus 22 times 9,8 sine of theta. And then we're going to divide both sides by a negative 22, just like that, and this will give us sine theta equals to divide by 22 times 9,8. That gives us a value of 0,478386, just like that. So I just rounded it off. So now from here we can be able to get our theta. So theta will be given by arc sine 0,478386. And then the answer, I think, will be 28,5 28,58 28,58 degrees. So that's how you get to your theta that way. So every time you have a question that wants you to calculate a certain quantity, all you need to do is to make sure that you write equations that are going to produce the unknown. The unknown in this case was theta, and I tried by all means necessary to make sure that I have theta as part of my equations, so that I can be able to solve it in that way. So now we succeeded in calculating the theta. So it's 28.58. I hope we'll have this in mind. And then let's try to answer the second question, the question that follows. So the question that follows is 2.4. So in 2.4, we are told that a force of 172 newtons is now applied on the 22 kg block, and the system of the blocks accelerates down the slope, right? So remember, this system was not accelerating, it was just moving at a constant velocity. So now a force is applied, and then these things start to accelerate down the slope, right? So the 22 kg is the one that is accelerating down the slope, obviously. And then they say the kinetic frictional force acting on the 22 kg block while it accelerates, that one remains the same. So the frictional force remains the same, right? What changed here is the acceleration. So it's accelerating at a different acceleration. I can put it in that way. So now 2.4.1, they're asking you to explain why the kinetic frictional force remains the same even though the system accelerates. Why does the kinetic frictional force remain the same? Why does it remain the same even though this thing accelerates for 2 marks, right? So the reason that we can give here, guys, is very simple. The kinetic frictional force, which is the Fk, is calculated using this. So Fk is calculated using 2.4.1. It's calculated by micro K times the normal force. That's the formula to calculate our frictional force, right? So our normal force in this case of the incline, remember we were in an incline, right? The normal force in this case, you know, from the free body diagram, it will be balanced by the Fg perpendicular in that case. So this is the same as micro K times mg cos of theta. So that's the formula to calculate the frictional force or the kinetic frictional force. So what we see here is that the kinetic frictional force depends on the micro K, which is the coefficient of kinetic friction, and also depends on the angle, which is what the angle of inclination. So what they did here, they only applied the force and the acceleration changed. But the angle of inclination remained theta, and also the coefficient of kinetic friction was not changed because the coefficient of kinetic friction is the nature of the surface. So the nature of the surface and the angle of inclination will not change. So that's why the frictional force remains the same. So the reason that we give here is that the angle of inclination and the nature of the surface remain the same. They remain the same. So if the nature and the angle of inclination don't change, for sure the FK won't change. So that's the reason that they wanted. Obviously, they want you to talk about the angle of inclination, you get a mark for that, and also talk about what the nature of the surface remaining the same. So that's how you get your 2 marks. Then 2.4.2, it's the calculation of the acceleration of the system of blocks. So this is the main question. So as you can see, it's 6 marks, right? So how do you answer this one? So to answer this question, it's very simple, guys. And in a way, you can be able to cram the procedure of answering these ones, especially the ones that comes with 6 marks or 7 marks in your exams. So it's either they're going to ask you to calculate the tension or they're going to ask you to calculate the acceleration, right? So what we see is that if you apply a force to the 15 kg block upward, the tension is going to change, right? The tension is going to change, so it means that this new setup produces a new tension. So it means you're not going to use the tension that you calculated in the previous question. So here's the procedure of answering such questions, especially those ones that comes with 6 marks. There's a way of answering this, and it's the simplest one, and it does not change. So what you're going to do is that you're going to draw a free body diagram for the two objects on a rough sheet. So after drawing the free body diagram of the two objects on the rough sheets, you need to write their F-net equations. And you're going to be having two unknowns, which is the acceleration and your tension. So if you have two unknowns, it means that you're going to use simultaneous procedures to solve your acceleration. So that's it. So that's what we're going to do. So obviously we know the F-net for the 22 kg block. So the F-net for the 22 kg block, we know it's given by, so now we're going to say 2.4.2 for the 22 kg block. The F-net, in this case, will be given by MA, right? So it's no longer zero because this thing is accelerating, right? So there's a certain acceleration, so you can't control that it's zero in this case. So you just need to write the forces that are involved here. So if you remember from what we drew, um, we had our frictional force, we had our F-net, we also had our tension in that fashion, right? So I think we can take down as positive, and why am I taking down as positive? Because I'm told that this thing, it accelerates down the slope. So I'm going to take the direction of motion as positive. So I'm going to take down as positive. So this down the slope as positive. So don't forget to choose direction every time you're answering these questions. So we're gonna have our, okay, so this is, it's a little bit tricky now. So if I can draw the free body diagram of this, it will be like this. I have my FG, my normal force, and my tension, right? And just because this thing, guys, is going down the slope, this means that the direction of friction also changes. So the friction is no longer acting downwards, it's acting what? Up the slope. It's acting up the slope because friction will always oppose the direction of your motion. So you have 1, 2, 3, 4 forces acting just like that. And not forget our components, our FG parallel, and also our FG perpendicular in that case. So now, as I've indicated, that we're going to look at forces that are in line with motion. And the forces that are in line with motion are what? FG parallel, FK, and our tension. So everything that goes down will be positive. So what will be positive will be FG parallel positive plus minus F of K plus minus tension equals to MA. So the MA is the mass is 22, and then acceleration is the unknown. So that's the first equation that we have. So our FG parallel is mg sine theta. So it means that we're going to expand this to be mg sine of theta minus fk. So they told you that the fk remains the same. So the fk is 43.86. So what changed with the fk is the direction because of the direction of motion. So it's minus 43.86 minus t equals to 22a. And then now we have to substitute our mg sine theta so that we can have a complete equation. So mg sine theta is 22, 22 times 9.8 sine of, the angle that we got was, I think we got an angle of 28, 25, we got 28.58, right? So sine of 28.58 degrees minus 43.86 minus t equals to 22a. So we can simplify our equation here. If we simplify our equation, we'll end up getting sine 28,58 minus 43,86, and that will give us, I think, an answer of about um, 59,27988 minus t equals to 2a. That will be our equation 1, right? So that's the procedure. Always write your FNet for the two blocks, and then you get your two equations, and after getting your two equations, you can solve that simultaneously. So now we're going for the 15 kg block. So for the 15 kg block, we have a free body diagram, obviously. Let's try to draw the free body diagram. So the free body diagram will have our tension going up. We also have our Fg going down. And also remember that we have a force of 172 that is being applied in an upward direction, right? So this force of 172 it's also included. So this one is going up just like that. So we can call it F applied. And that's our new free body diagram. So we do the Fnet for this one. So Fnet still remains MA. And then we're going to take upward as positive in this case because we see this thing is moving up. So we take up as positive. So if we take up as positive, we'll have Fnet being equals to positive T plus positive 172 minus um, mg. So that's our force of gravity. Mg equals to, the mass is 15 times acceleration. So our tension is unknown, and then we know T plus 172 minus 15 times 9,8, which will give us 15A. And then this will give us 172 minus 15 times 9,8 will give us 25. So this is T plus 25 equals to 15A. So this becomes our equation 2. So we have two equations now, equation 1 and equation 2. And what we have to do is to get our A, right? So what we can do here is to eliminate the T because we're trying to calculate A. And how can we eliminate T? We can add equation 1 and equation 2. So add equation 1 and equation 2. So if we add these two equations, the plus T and the minus T will cancel, right? And that will be eliminated in that case. So let's try to add equation 1 and equation 2. So it means we're going to add 59,27988. We add it with 25. It will give us 84,27988. And then we add the negative T and the positive T, it will give us a 0. And then we're going to add the 22 and 15. So 22 plus 15 will give us 37A. And then to calculate our A, we'll have to divide both sides by 37. And we get 84,27988 divided by 37 will give us an answer of 2,0 uh, 2.8 meters per second squared. 2.28 meters per second squared, right? So that's how we calculate the acceleration, right? So of the system. So that's the acceleration of the system. So if this question wanted you to calculate the acceleration of one of the blocks, let's say it wanted you to calculate uh, the acceleration of the 15 kg block. So the 15 kg block has its own direction of its the motion of the 15 kg block has its own direction. So if it was the acceleration of the 15 kg block, you would say it's 2.28 meters per second squared upward. Why are you including direction? You're including direction because acceleration is a vector, and whenever you calculate a vector, you need to include its direction. So in this case, we did not include direction because they wanted us to calculate the acceleration of a system. So it's the acceleration of the 22 kg block and the 15 kg block. So these two things are going in different directions. So we can't have a single direction, right? So that's how you answer questions for Newton's laws. And that will be question two, even in your test tomorrow. Those that are writing their prelims, you'll get it in question two. All you need to do is to make sure that you have all the laws and you understand the applications, right? So now we're going to go to question five, um, which is work, energy, and power. And we'll just answer a few questions and also remind you of maybe the concepts that are there, right? So we'll start work, energy, and power in 2 minutes. So in these 2 minutes, what you can do is to maybe share the live proceedings, uh, subscribe to the channel if you haven't subscribed, so that you help us grow and we reach many people that might also benefit from this. So at the meantime, we can be sharing and also subscribing to our channel in that way. And don't forget to post the questions that we have, right? So if you had a question on how I did question two, or if there's something that you don't understand, you are also allowed to post the questions. Okay, now we are back with question 5, that is work, energy, and power. And we're going to be looking at a question paper from, I think, from the Eastern Cape, or still the Eastern Cape, right? We're going to be looking at the very same paper, it's a trial paper, and we're going to be answering question 5 together. So, in this chapter, work, energy, and power, obviously you're going to be asked questions on work, questions on energy, and questions on power, right? So all you need to know here is to know the formulas, and you also know how they come about and their application. It's very simple, right? So I'm gonna simplify this in few minutes, and whatever that I will tell you in this proceeding, that's how you're going to answer all the questions that you'll get in work, energy, and power. So as you can see in question 5, we are told that, or we're given a skateboarder, and we're told that a skateboarder skates from point A of the track, which is which is at a vertical height of 15 meters, and aims to come to rest at point D. So the aim is to come to rest at point D. On the other side, on the as shown on the diagram, section AB is frictionless. So now you're being told that section AB is frictionless while B, C, and CD are rough. The combined mass of the skateboarder and the skateboard is 55 kg. The skateboarder experiences a frictional force of 50 newtons while moving from point C to point D. Ignore the effects of uh, air resistance. So we're gonna do the very same thing that we did with the question 2 that we just answered. So we're going to identify important points that were given, right? So in work, energy, and power, when we are told that a certain section is frictionless, okay, AB is frictionless, that's what we are told, frictionless, so there's no friction. So if there's no friction, it means that uh, there's one non-conservative force subtracted, right? So that's what we know, because friction is it's a non-conservative force. Okay, and then again we are told that BC and CD are rough. So BC and CD are rough. It means that we have friction in BC and CD. And now we're also told to ignore the effects of air resistance. So the first question that we have here is a question that requires us to state the principle of conservation of mechanical energy. To state the principle of conservation of mechanical energy. So this is simple that the total mechanical energy in an isolated or closed system is conserved or remains the same, right? So that's the definition that's going to give you 2 marks. So it is very important here to understand the words isolated and closed system, right? And I'm going to define them in terms of grade 12, right? So this is not a proper definition for isolated or closed system. It only applies in grade 12 and especially in this chapter. So every time when they talk about an isolated system is a system without non-conservative forces. So a system that does not have non-conservative forces, that system is isolated or closed, right? So what are your conservative forces? Your conservative forces are the likes of applied force, friction, your tensions, etc. Right? So those are the non-conservative forces. So if a system does not have an applied force, does not have a friction force, does not have tension, it means that that system is what? It's isolated. And if the system is isolated, it means that you are allowed to apply the principle of conservation of mechanical energy. So the principle that you just stated above can be applied in that system. It can only be applied in a system where there are no non-conservative forces. I hope that is fine. So let's look at 5.2 and see what they want. So in 5.2, they want us to calculate the kinetic energy of the skateboarder at point B. Calculate the kinetic energy of the skateboarder at point B. Let me erase this. This is part of your notes, not part of your answer. So 5.2, we have to calculate the kinetic energy at point B. So what you can do now is maybe for 30 seconds, just try to think about it and see how you are gonna answer it if maybe you are alone or maybe you are in an exam, and then you will correct as I do it. So try to look at uh, 5.2. So let's see. It's for 3 marks, right? And I know a lot of people, um, it's written in your mind that when you see 3 marks, you only think about formula substitution answer. That is not always the case. It's all about a formula substitution answer. You need to analyze. So in question 5, and especially in work energy and power, usually the law that you state is the law that you apply in the next question, right? So now, if you want to calculate the kinetic energy of the skateboard at point B, for example, for you to be able to calculate the kinetic energy, EK, you need to know half the mass and the speed, right? But you don't know the speed at point B. So that becomes a hindrance. And if you don't know the speed, it means that you can't use this formula to calculate the kinetic energy, right? So why don't you try to use the law or the principle that you stated in 5.1? So the principle that is stated in 5.1 is the principle of conservation of mechanical energy. And why you, you are allowed to use this principle? The reason you are allowed to use this principle is because from point A to point B, the system is isolated. Why is it isolated? Because there is no friction, there's no applied force, and also there's no tension. So there are no non-conservative forces from point A to point B. So if there are no non-conservative forces, it means that this is an isolated system. And if it's an isolated system, you can use the principle of conservation of mechanical energy. So the principle of conservation of mechanical energy states that the total mechanical energy at point A is equals to the total mechanical energy at point B, right? So the mechanical energy at point A is simply given by the gravitational potential energy plus the kinetic energy at that point. So now we're going to say this is half mv squared at A plus mgh at A will give us half mv squared at B plus half, no, sorry, plus mgh at B plus mgh at B. So now we're going to substitute your stuff here. So what we see is that we need to know the speed at A or the velocity at A. So let's go back to the statement above. So in the statement above, we're told that a skateboarder skates from point A of the track, which is that, and then the aim is to come to rest at point D. So the aim of this guy is to get at rest at that point, right? So we're not given the the speed. So if we're not given the speed, it means that this guy had a certain speed, and we need to determine that. So what we're going to use is that I think in this question somewhere here they were supposed to tell us that this guy started from rest, right? So I think that's what it's missing in this question. This guy started from rest, so you need to add that. He started from rest. So yeah, so I think that's a statement um, that it's missing, and I think it's part of the errata. You can also go to the internet and download the errata, and I think something like that will appear. So this guy started from rest, so that's what we're going to use in this video. So if this guy started from rest, it means that the kinetic energy at A, because the speed is 0, it will be 0 plus the mass. You're going to use the combined mass, and then the combined mass is 55 kg times 9,8 times the height at A, which is 15, right? Equals to half the mass. So now, here I've expanded the kinetic energy, but you realize that the expansion of the kinetic energy will eliminate the quantity that we're looking for. So what we can do here is to simply write our EK as the EK at point B, because that's what we're looking for. So the half mv squared B will be EK at B, and then plus mgh at B. So the mgh at B at this point will be 0 because the height is 0. So anything times 0 will give you a 0. So that makes the gravitational potential energy at point B to be 0 in that case. So therefore, the kinetic energy at B will be given by 55 times 98, 9,8 times 15. 55 times 9,8 times 15. I think that will give us an answer of 8,085 joules. So that's the kinetic energy at point B. So don't forget to write the formula. And then now we have to go to the next question. 5.3 requires us to state the work energy theorem. So this is the part where the chapter starts to be interesting, right? So they want us to state the work energy theorem in words. And I'm sure you can see that you get a lot of marks, or you get a lot of marks through stating, right? Through stating and defining terms. That's where you score a lot of marks. So the work energy theorem, it's W net equals to change in EK. So this is a theorem that states that the total work done on an object, the total work done on an object, or you can say the work that is done by the net force on an object, is equal to the object change in kinetic energy. So that's how I've written in the above formula. So that's how you state your work energy theorem. And for stating it like that, you get 2 full marks. So you don't have to be losing uh, your marks uh, from definitions. So 5.4, they say you use energy principles to calculate the kinetic energy of the skateboarder at sea, and then also to calculate the magnitude of the frictional force along BC that will enable the skateboarder to come to rest at point D. So, energy principles. So, what you need to know, guys, you need to know all your energy principles, or you need to know that when they say you have to use energy principles, you need to know which principles to use, right? And what's and then just like that. Okay, so our energy principles, guys. So when they talk about energy principles, the formulas that needs to come to your mind is one, WNC equals to change in EK plus change in EP. That's the first formula. Two, W net equals to change in EK. And lastly, it's um, the mechanical energy. So E mechanical initial equals to E mechanical final. So these are the 3 formulas that they want you to use, right? So what we see here is that for sure we can't use the third formula, because the third formula is the principle of conservation of mechanical energy. And now they want something, or a quantity for point C, and you know that BC is rough, right? This is rough and also rough. So for these rough surfaces, we can't use the principle of conservation of mechanical energy, because the system now is no longer isolated. So it means that we're going to use equation 1 and equation 2 to be able to answer our equation. So let's start with equation 2. Okay, let's start with equation 2. So equation 2 says that W net um, W net equals to change in EK. So what they want here, they want the kinetic energy at point C, right? So when we apply this formula, W net equals to change in EK, it means that we're going to look at point B and point C. So point B will be our initial point and point C will be our final point. So if we can get the EK final, it means that we have the kinetic energy at point C. So this is what we're going to do. Now we simply substitute our formula. So W net, you don't have to forget that W net is the total work done on the object, or the work that is done by all forces acting on the object. So for you to get W net, you need to also know the forces that are acting on the object that as it moves from B to C, right? So as this thing moves from point B to point C, we can see that there's only force of gravity acting, the normal force is there, and also frictional force. And what do we get that? We got it from the information that we have above. So from the information that we have above, we are told that the skateboarder experiences a frictional force of, okay, now they gave us the frictional force as he moves from point C to point D, right? And then it means, okay, we proceed with that. It's fine. So we have that frictional force is acting also at point B. So it's a force that is going in this direction, F of K. And then this means that W net from point B to point C will be given by Fk only, because uh, normal force won't do work and Fg won't do work. And the reason they are not doing work is because these forces, they are perpendicular to the motion. So it means that our W net will be the same as Wfk equals to um, change in Ek. So change in Ek is minus half, sorry, not minus half, it's half mv squared final minus half, um, so let me write it like this. Because remember, we don't have to forget what we're calculating. We're calculating the kinetic energy. So I'm just going to write Ek final minus Ek initial. We don't have to forget that. And this Ek final is the term that we're calculating for. And then Ek initial is half mv squared initial. And then now we have our Wfk, right? So we need to know the magnitude of the frictional forces acting at this point. Okay, so one thing also, I was checking the errata. So the kinetic friction acting from point C to D is the same as the one from B to C, right? So from B to C, uh, BC, also there is a 15 Newton force acting that way, right? So that's the development that uh, uh, I got from the errata, because I can see that this question it was going to be a very difficult one to answer without knowing our frictional force in that way, right? Okay, so okay, so let's see how we answer this question. Um, okay, so we are calculating the kinetic energy at point C. Okay, so we chose to analyze point BC. Okay, let's see. Um, if we take point BC as our path of study, it's going to be difficult because, again, it's not making sense why BC it's also 15 newtons, right? Can't be the same frictional force on a horizontal surface and a straight and an inclined surface is like that. There's still that problem that it's not making sense to be having two equal frictional forces on different surfaces. So what we can do here, we can simply change the path. We can simply change the path. So if we change the path, it means we're going to consider point CD, right? So let's consider point CD, because I think for point CD, that's where we have almost everything. So let's look at point C and D. Okay, so when we consider point CD, still looking at uh, W net equals to change in EK, we will realize that our F net or our W net will be given by the sum of the work that is done by the individual forces. So we need to get the individual forces. So the individual forces acting here are our Fg that is going down. We have our normal force, Fn. We also have uh, our frictional force. So since this thing is moving up, so the frictional force will be going down just like that, F of K. So that's our free body diagram, right? And then we don't have to forget that from our free body diagram, we also have the components of the weight Fg perpendicular, and also we have what? Our Fg parallel in that case. So that's what we have. So we know for sure that, so if we draw the components, we might erase the main force here. So that's our free body diagram, just like that. With our Fg parallel and that. So we can see from our diagram here that our Fn is not doing work. We can also see that uh, Fg perpendicular won't do work because these are perpendicular to the motion. So the only forces that will be doing work here are Fg parallel and Fg and F of k. Sorry. And then it means that W net will be given by the done by work done by Fg parallel plus the work that is done by uh, F of k equals to Ek final minus Ek initial. So what we're looking for, we're looking for Ek final initial. So sorry. So if we consider point CD. Point C will be our initial point, and this one will be our final point. So therefore, we are looking for EK initial. We have our EK final in that case. So I forgot that we changed the path. So it's CD. So our WFG parallel is given by mg sine of theta, which is for the force, times change in x, which is the displacement, times cos of theta, plus f of k times change in x times cos of theta equals to ek final. So ek final will be 0 because remember the aim of this uh, skater is to be at rest when he gets or to point D. So he wants to be at rest when he gets to this point. So if he's at rest, it means that his speed is 0. And if his speed is 0, it means that the final one will be a 0 here minus EK initial. So we're going to substitute our mg sine theta, which will be a 55 times 9,8 times sine 15 degrees times 10 meters cos of. So the angle between FG parallel and the direction of motion is 180 because this thing is moving up the incline. So the angle is 180 degrees plus kinetic friction of 50 newtons times the distance still 10 times cos of 180 because they are opposing motion, which is equal to minus EK initial. And then now you need to get the value of EK initial. So if you press your calculator and check the value of 9,8 sine 15 times 10 and then plus 15 times 10 and then the value of EK initial will give us 1545.03 joules. So therefore, the EK at B will give us 1545.03 joules. So you saw that we use the path CD to calculate the kinetic energy at B, and if you use path CD, the kinetic energy at what am I doing? Am I doing on 8 point what? At point C. Okay, yeah. Oh, sorry. It's not the kinetic energy at B, it's the kinetic energy at point C. Because as you can see from the diagram, the initial point here is point C. Sorry about that. Okay, so let's look at the last question, 5.4.2. And to answer this question, it's very simple and use the same procedure to almost all the types of questions that you'll get in your exams for question 5. So the last question wants us to calculate the magnitude of the frictional force along BC that will enable the skateboarder to come to rest at point B. So they've given you a condition. A condition is to make sure that the skateboarder is at rest at point D. You need to calculate the magnitude of the frictional force. So remember, with all the calculations that we have done so far, we've been working with that condition that the skater will be at rest at point D. So it means that also here you need to work with that assumption that this guy will be at rest at point D because that's the requirement. So still they said that you need to use energy principles. So to use your energy principles, you need to use obviously W net equals to change in EK or WNC equals to change in EK plus change in EP. So in this case, I would use WNC. And the reason why I'm using WNC is because uh, they want the magnitude of friction, and friction is a non-conservative force. So for 5.4.2, I'm going to use this principle. WNC equals to change in EK plus change in EP. So now we're no longer looking at path CD, we are looking at path BC, right? So they want us to calculate the magnitude of f of k at BC. So we want f of k at BC. So we're gonna have a free body diagram like the one that we drew before. So we're gonna have dot, normal force, force of gravity, and f of k. As I said, normal force won't be doing work, weight won't be doing work, and then the only force that will be doing work will be f of k, right? And again, f of k is the only non-conservative force acting. So this means that WNC will be given by WF of k, because f of k is the only non-conservative force doing work. So WF of k will be equals to change in EK. This is EK final minus what? EK initial plus EP final minus EP initial, in that fashion. So now we have that equation that we try to expand. But the problem that we have now is that we haven't produced the variable that they want. The variable that they want is f of k. So it means that we have to expand WFK to give us our f of k times change in x cos of theta equals to the kf final. When we consider point path BC, the ek final becomes the kinetic energy at C, and then the initial one will be the kinetic energy at B. So the kinetic energy at B is the initial point, and then the kinetic energy final is the kinetic energy at C, and we have these two values. So the kinetic energy at C, I think we got 15.45,03 minus initial. That's the kinetic energy at B. We got 8085 joules, remember, in question 5.2. And then the change in potential energy. So we can see that looking at path BC, the height is 0. So it means that the initial height was 0 and the final height was 0. So therefore, the potential energy at B was 0 and the potential energy at C was also 0. So the change in kinetic energy will give us a 0. So EPF minus EP initial will give us a 0. So we don't worry about that. So it's the answer there, we're going to be left with 45,03 minus 8085. And this will give us a value of minus 6539, comma 97. 97. And then we'll substitute our f of k on the other side. So if we substitute the f of k on the other side, it's f of k is the unknown that we're looking for. The change in x is 10, and then cos of theta. So the cos will be cos 180 because friction will always oppose motion. So therefore, this will give us minus 10 f of k equals to minus 6539, comma 97. And you're going to divide both sides by minus 10. And if we divide both sides by minus 10, we get an answer of 653, comma 9965. This can be simplified to be 654 newtons. I think that's the answer that we're getting. Can check the answer. Okay, so that's a few steps of answering your question 5, which is work energy and power. So my advice to you is to take your time as you analyze your questions, because you saw that you can make mistakes easy. And then in 2 minutes, we'll start electric circuits. And I remember electric circuits is one of the topics that most of you requested in that way. So we'll come back in 2 minutes and continue with electric circuits. Okay, welcome back. Um, we'll continue, and I think this will be our concluding chapter, which is electric circuits, and we'll be looking at a question paper. It's a national paper, a supplementary uh, paper from 2016, and we'll just look at question 9, which was having 15 marks. So, um, as you can see here, we are given a circuit diagram uh, with a battery of an unknown EMF and an internal resistance of 0.5 ohms. So it's connected to 3 resistors. So we have the resistors there, the 4 ohm resistor, we also have the 8 ohm resistor and the 2 ohm resistor. They're saying a high resistant voltmeter and an ammeter of negligible resistance as shown below. So the voltmeter has a high resistance and an ammeter of negligible resistance. So uh, if the voltmeter has high resistance, it means that there's no current that is passing through the voltmeter, and then the ammeter of negligible resistance, it means that we assume that there's no resistance in the ammeter, so all the current passes through there freely without any form of resistance. So that's what they've given us. So now, before I start answering this question, I would like to indicate that you need to always remember that in grade 12, you have an internal circuit and an external circuit. So the external circuit is it's sorry. Before I continue, I think I once did this question. Did I do this question in the YouTube channel? Let me check something. I think I did this question in the YouTube channel, if I remember very well. So I'm just gonna see if I did this question or not. Okay, it's fine. I did not do the question. I thought I did it in the YouTube channel, and I was gonna change the question. So I did not do it. So it's a new question. So before I start answering, what I can indicate is that we have two circuits: the external circuit and the internal circuit. So the internal circuit is the circuit inside the battery. That's where we talk about our internal resistances, and the external circuit is the circuit outside the battery. That's where we talk about our external circuit, right? So we have the internal circuit. So the internal circuit, that's where we talk about the internal resistance. So there's small letter r. And the external circuit has the external resistance. So the external resistance is the capital letter R, right? And then obviously we have the current of the circuit. So the total current of the circuit is given by capital letter I. So we also have the formula E equals to I times R, which is the external resistance, plus R, which is the internal resistance, in that way, right? So if we expand this formula, we have capital letter IR plus IR, small letter r. So this is called the V external. This is the external voltage. And then we also have internal voltage. So internal voltage sometimes is called the V loss. So it's there. lost voltage, right? So the lost voltage is the internal voltage, and then V external, sometimes it's called the potential difference. So every time in electric circuits, when they talk about the voltmeter reading, when the circuit is closed, so when the circuit is closed, the voltmeter reading across the battery reads the potential difference. The potential difference they're talking about is the V external, which is calculated by I times capital letter R. So we have an EMF. So an EMF is the electromotive force, right? So this is the constant voltage. So it's the voltage of a battery that is constant. It does not change. So this is the maximum energy that is supplied by the battery. So that's the maximum. So if the maximum is 13, it will remain 13 up until the battery is used up, just like that. So that was a few things to remind you. And then the rest, you need to remind yourselves of the Kirchhoff's laws, which are the laws of what? Of parallel connections, laws of series connections, stuff like that. So that's what you need to remember, that in a parallel circuit, current is divided and the voltage remains the same. And in a series circuit, voltage is divided and current remains the same. So that's what you need to remember. And let's see how we're going to use the information that I just shared with you to try and answer this question uh, 9.1. So in 9.1, you are asked to calculate the reading on the voltmeter. So that's our voltmeter there. So what we see is that the voltmeter is connected in parallel to the battery there. So it's 9.1.1. So it's for 3 marks. So we also told that the current or the ammeter reading is 0.2 amps. So this is 0.2 amps, right? So they want us to calculate the voltmeter reading. So what you have to know is it's that the voltmeter reading across these two terminals, if you were to connect a voltmeter across these two terminals, the voltmeter reading across these two terminals will be the same with the voltmeter reading that will be displayed here. And the reason is that this branch is in parallel to everything that is in the circuit. So if it's in parallel with everything that is in the circuit, it means that the voltage will be the same, right? So we can calculate the voltmeter reading of this branch because we know the resistance and we also know the current that will pass in this branch. So the current that will pass in this branch is 2 amps, and then the resistance of this branch is given by 4 plus 8, and that is 12. So V in that branch is equals to IR. So the current is 0.2 times 4 plus 8, and that will give us an answer of 2.4 volts. So the voltage of this branch is 2.4 volts. So if the voltage of this branch is 2.4 volts, it means that the voltage of everything connected parallel to this branch will be 2.4 because voltage remain the same in a parallel connection. Okay, so therefore that's the voltmeter reading. 9.1.2, They want us to calculate the total current supplied by the battery. So to calculate the current total circuit supplied by the battery is to understand that the direction of current will move from the positive terminal also. And when it gets to this junction, some of the current will go up, right? So this is the movement of current. And then some of the current will go down. And this is the 0,2 current. And when it gets to this point, it goes back to the negative terminal. So there's the direction of current. So it's understanding that there's a portion that goes to the 2 ohm resistor, and then there's a portion that goes to the resistors that are connected in series below the battery. So now that we know the the current that goes to the the 4 ohm and 8 ohm resistor, we need to calculate the current that goes to the 2 ohm resistor. So don't forget that I said that the voltmeter reading across this voltmeter is 2.4 volts. So this means that also the voltmeter reading for the 2 ohm resistor will be 2.4 volts. And reason being is that they are connected in parallel to this branch. So we know the voltmeter reading for the 2 ohm, so therefore we need to calculate the current. The current will be given by V over R. So the voltmeter reading there is 2.4, and then the resistance is 2, and then the current will be given by 2.4 divided by 2. That will give us 1.2 amps. So it means that the current that goes to the 2 ohm resistor is 1.2 amps. So we know that there's a current of 1.2 amps, right? So they want the total current that is supplied by the battery. So the total current that is supplied by the battery is the 1.2 amps plus the 0.2 amps. So the total current is given by 1.2 plus 0.2 equals to 1.4 amps. So that's the total current that is supplied by the battery. And I hope that made sense. Okay, so let's look at question 9.1.3. So 9.1.3, they want us to calculate the EMF of the battery. So what we have now, we have the total current, and we also have the internal resistance we're given. What we don't have is the external resistance, which is the capital letter R. So it means that what we're going to do now is to calculate the R external, which is the external resistance. So this is the resistance of everything outside the circuit. So we have we have 3 external resistors. This one, the 4 ohm, and the 8 ohms. So the R external, so 4 ohm resistor and the 8 ohm resistor, they are connected in series to each other. So these can be added to produce one resistor, which will be a 12 ohm resistor. So we have this, the 2 ohm resistor connected in parallel with the 12 ohm resistor. So what we did there, we simply added the 4 ohm resistor and the 8 ohm resistor because they're in series to each other, and then they produced the 12 ohm resistor. So to calculate the R external here, it means that we're simply going to say R external, which is the capital letter R from the EMF formula, will be given by R1 times R2 over R1 plus R2, because now we have two resistors, equals to uh, 2 times 12 over 2 plus 12. And this will give us an answer of 2 times 12 over 2 plus 12, give us an answer of 1,7 1 ohms. So this is our R external, and it's so small because um, it's a parallel connection. So a parallel connection decreases the R external, as we know, right? So now we have our R external. So if we have our R external, we can simply calculate our EMF as EMF equals to I R plus small letter r. And then the current that we have here is the total current of the circuit, which is 1,4 times the R external is 1,7 plus the internal resistance is given to be 0,5, and then the EMF is 1,4 times 1,7 plus 0,5, which will give us an answer of 3,0808 volts. So that's how we calculate the EMF in this question. So let's go to question 9.2. So in question 9.2, they asking us how will the voltmeter reading change if the 2 ohm resistor is removed from the circuit. Write down increase, decrease, or remain the same. So you're making a change to the circuit, and the change is removing a resistor. So I'm going to show you how to answer these questions. So to answer these questions, it's very simple. So let me erase what we wrote here. Let me erase this. So guys, this is how you analyze these questions. The first thing that you must check is the change that you are making. You are removing a resistor, and that is an external resistor, by the way. If you remove an external resistor, what is it that you're doing? You are changing the external resistance. So what we come and check is that when you remove a resistor, what happens to the total resistance? So if you remove the 2 ohm resistor, it means that you only be left with 2 resistors that are connected in series, right? So if you remove the 2 ohm resistor, what you see is that the R external, or the capital letter R, will be given by 4 plus 8, and that will be 12 ohms, right? And remember, the total resistance of the circuit, we got 1,4 something in the previous question when we had that connected in parallel, right? But now when you remove the 2 ohm resistor, you realize that the total resistance of the circuit increases, right? So that's a note that you need to make. The total resistance of the circuit increases, right? And now they're asking about the voltmeter reading. The voltmeter reading is the V external. So you're going to use this formula to answer this question. E equals to I R, which is plus I small letter r, stuff like that. So this is our V external plus IR equals to E. So they're asking you about the voltmeter reading. So the voltmeter reading is the V external. So you need to make V external subject of the formula. So this will be E equals minus IR equals to V external. Okay, so you're going to analyze it using this. So they say you choose from increase, decrease, or remain the same. So what I'm going to do here, I'm gonna explain the answer first, and from the explanation, I'll be able to draw my conclusion. So 9.2. So what we see is that in 9.2, um, the total resistance of the circuit increases. That's what we have observed because we removed that. So the total resistance of the circuit, so it's the total external resistance. Talk about external resistance. External resistance of the circuit increases, right? So when the total external resistance of the circuit increases, what will happen to the current? The current, the total current will decrease, right? So that's the relationship between resistance and the current. So when the current decrease, what does that tell you? So this tells you that the V loss, which is uh, I times small letter r, will decrease. So the internal voltage or the V loss decreases. Or one. So if the V loss decreases, it means that you're going to subtract a lesser value from the EMF to get the V external, which is the voltmeter reading. So if you are subtracting a lesser value to a constant EMF value, the V external therefore will increase. So the correct answer here is increases. And those are the reasons that you give. Increase, a mark for that, and then a mark for this and for that. So that's how you answer this question. So firstly, you need to understand what happens to the total resistance. And after understanding what happens to the total resistance, you also need to check what happens to the V loss. And after checking the V loss, obviously, you look at how that will affect your external resistance. So we're done with electric circuits, and I would have loved to do more questions with you. And I hope you benefited from this session. And I hope to see you next time when we prepare for Physical Sciences Paper 2. Hopefully, we're going to be looking at organic chemistry, acid and bases, and chemical equilibrium. So good luck on your prelims for those who are going to write tomorrow. And don't forget to share the video and subscribe to the channel and help us grow. Thank you.